third lecture, and in this we propose to solve the problems that I set in minor 1 examination, and then if time permits we would look at two other parameters of the 2-port, namely hybrid and transmission parameters. Minor 1 consisted of 3 questions. 25 was the total marks, and the first question, question 1, related to this network. No, it's the other way around. T equal to 0, the switch is opened, there is a battery E, and there are two parallel branches R and L. The value of L is CR squared, it is a special value, and this current is I. Then there is a resistance R. Note that these two resistances are equal, and this capacitance is C. The voltage across this combination is V. The switch has been in the on position for a very long time, and at t equal to 0 the switch is thrown out. What you are required to do is to find out the current I of t and V of t, the voltage V of t for t greater than or equal to 0 plus. This is the question. Now the question is, as you can see, it is a combination of initial conditions in inductor as well as the capacitor, but the element values have been very carefully chosen, cleverly chosen. As you shall see, this is a very interesting example, and writing differential equations, well, you would be able to solve it, but since Laplace transform converts differential equations into algebraic equations, there was no point in writing differential equations. A few of you did try to write the differential equation. Number 2, the first thing we do is to find out the two currents, find out the initial conditions. I of 0 minus is obviously equal to E by R. If the battery is here for a very long time, the inductor acts as short, and therefore the current through the inductor is I, and the Vc 0 minus, this voltage Vc 0 minus is obviously equal to capital E, because there is no current in this arm in the steady state, and therefore the voltage across the capacitor must be Vc. Since we know the initial conditions, we can now draw the transformed equivalent circuit, Laplace transformed equivalent circuit. There are two options. We can either draw the Thevenin equivalent or the Norton equivalent. What we have to do is to find a current I of t and the voltage across the combination. This suggests that at t equal to 0 plus it is a single loop circuit. This suggests that you should use Thevenin's equivalent, not Norton's. Some of you have used Norton's and then did not know how to manipulate. Okay? The simplest thing would be to use Thevenin's equivalent, contain a loop as one loop only. Do not make it more complicated than what the circuit given is. And if you draw the transformed equivalent circuit for t greater than or equal to 0 plus, obviously what we have is R, and then the inductance is the inductance L, well, multiplied by S, okay, its impedance, and then you have a voltage generator. This is the Thevenin equivalent circuit in the opposite direction, that is minus plus L times IL 0 minus. IL 0 minus is E by R, and therefore L E by R. This is the equivalent circuit for the inductor. For the capacitor, and the current transform is capital I. For the capacitor, you have R, then an uncharged capacitor C in series with a voltage with this polarity, okay, whose value is Vc 0 minus divided by S because you are taking the transform, and therefore this will be E by S. Very few students got this problem correctly. Once you have drawn this equivalent circuit, things are absolutely simple. This voltage is V, let us say capital V, the transform voltage. And obviously, if you look at this circuit, it is a single mesh circuit, simplicity itself, capital I shall be equal to the total driving voltage divided by the total impedance. Total driving voltage, you see, there is a question of sign now. L E by R, this source, voltage source, tends to send a current favoring I, right, in the same direction, and therefore L E by R. Then this one, you see, minus plus, then minus plus, and therefore this should be added. E by S divided by R twice R, R and R, twice R plus SL plus 1 over SC. And if you simplify this, you simplify this with L equal to CR squared, normally you see this looks like a second order circuit, and therefore the denominator, after clearing fraction, after clearing from 1 by SC, inverse power of S, the denominator should be a quadratic, agreed. The numerator should be a first order term, but it turns out that one of the terms cancels out. The first order factor of the numerator cancels with one of the factors in the denominator, and simplification with L equal to CR squared, this algebra you can do, simply reveals that I is equal to E by R 1 over S plus 1 by CR. I write it in this form to be able to transform this back into the time domain easily, and therefore I of t is equal to E by R e to the minus t by RC ut.
So even if it does not cancel and carry out the whole procedure, then also it will lead to the same result.
Of course, but with a bit of more algebra. If you can substitute the value at the end, but if you did it right at the beginning, things become very clear. Things sort out very easily.
Shouldn't it be 1 over S plus 1 over CR square? Because the denominator in the term for I is a quadratic thing. So
yes,
it will have one pole only. So that will be.
That cancels with one of the zeros. You see, this is what I say. This special value of L makes the numerator factor, the linear factor, cancels with one of the linear factors in the denominator. So ultimately one factor in the denominator is left, and it is a single pole circuit. The circuit is called a degenerate circuit because even with two elements, two dissimilar energy storage elements, it shows only one time constant, and therefore it is a degenerate circuit. All right. The other part of the problem, that is capital V, the voltage across the combination is, as you can see, is simply E by S minus this voltage minus the drop in R and C. Why minus? Because the current flows in the opposite direction. So minus R plus 1 over CS multiplied by I. And if you substitute this value of I, it is very easy to see that this is identically equal to 0. That is, V of t is identically equal to 0. All right, this voltage is identically equal to 0. Now, as I said, this is one of the most interesting circuits, and I shall now, as an annexure to the solution of this problem. Meanwhile, is there a question?
Sir, at t equal to 0 minus, the entire current flow through
The resistance.
the inductor is short.
Right.
So the BC should be 0 at 0 minus, because all the charge through the capacitor will discharge through the inductor.
At t equal to 0 minus, the battery is there,
The battery is there and the inductor is short.
inductor is short,
So
yes.
all the current flows through inductor and there is no current through capacitor.
Correct?
So the
Capacitor is fully
should-
charged.
The capacitor should discharge through.
No, capacitor is fully charged.
Resistor, because of resistor.
Fully charged at t equal to 0 minus. The voltage across the capacitor is equal to E, and therefore there cannot flow any current through this resistor. Okay, and then as soon as the battery is disconnected, current has to flow. So it flows in the capacitor in the opposite direction to discharge the capacitor, and ultimately at infinite, after infinite amount of time, there is no current, and the voltage, even though a current flows in the loop, the element values conspire to make this voltage drop across the combination equal to 0. Now this is, as I said, one of the most interesting circuits of network theory, and if I draw this circuit again, R, L, R, C as an annexure to the working out of the problem, let me point out that if this is enclosed within a black box, let me look at the black color, okay. If this is enclosed within the black box and you have a resistor R also enclosed within a black box, call this box number 1 and box number 2, alright. By measurements from the terminals, it is impossible to tell which box contains one pure resistance and which box contains the inductance and capacitance. There is no way it can be done. This is one of the ways that people try to connect a battery and open it. But as far as external manifestations are concerned, suppose you connect a battery here. Suppose you connect a battery. The current at 0 minus would be E by R. Alright? At 0 plus, no current. Right? No current. In other words, what happens in this is whatever current flows in this branch, the negative of this must flow in this branch. You understand what I mean? So that the total current here is 0. And obviously, if there was a battery and the battery is switched off, the resistance cannot store any energy, and therefore the voltage is identically equal to 0. This happens with this circuit also. People have tried many different ways to distinguish between the two circuits. They have failed. Alright? And
Is this because the special value of the inductance?
that is correct. It is because of the special
the
value.
resonance frequency, I mean, it makes it resonate with all frequencies.
One of the poles cancels with one of the zeros.
Always.
If you find out the input impedance is identically equal to R. Identically equal to R. So the poles and zeros
But
cancel
if
each other.
we short the input terminals at 0 plus, would be correct.
Try it out. If you can do it, that would be news.
Sir, is this regardless of the kind of battery we are putting?
Regardless of the kind of, it could be a sinusoidal source. It could be a triangular voltage source. We don't care. It could be a current source. There is no way that it can be distinguished from. Question number 2. Question number 2 is, the first part was absolutely simple. There is no problem in this. L and C, there are no special values. This is V0. The question was, in the network shown below, write an expression for the transfer function, that is V0 by Vi, and I wanted in terms of zeta and omega n, zeta and omega n. And I also stated that zeta is less than 1. There were questions in the exam hall, why this is not needed? Why is this redundant information? Okay, life is full of redundant information. You can take it or leave it. Okay, it's given, but it was not redundant here, because if zeta is not less than 1, then you would not be able to say that the poles are complex. Okay, so this is an useful information, and by simple algebra, it is easy to show that the transfer function is s squared plus twice zeta omega ns plus omega n squared, where omega n squared is equal to 1 over LC and zeta is equal to R by 2L. Is that right? Zeta omega n is equal to r by 2n. Is it okay? All right. So this part is absolutely fine. The part which baffled you, should not have baffled you, but it did, is the sketch of poles and zeros. You see, if you look at the transfer function, obviously the zeros are 2 in number, twice zeta omega n s plus omega n squared. The zeros are obviously at s squared equal to minus omega n squared, and therefore this should be s equal to plus minus j omega n. Okay, there are a few who plotted the zeros on the real axis, one at minus 1 by square root LC and one at plus 1 by square root LC. Obviously that is unpardonable, because s squared plus omega n squared equal to 0 has the solution s squared equal to minus omega n squared, and if you want to take the square root of minus 1, it has to be j, plus minus j. These are the zeros. The second thing that baffled you was the poles are obviously at minus zeta omega n plus minus j omega n square root of 1 minus zeta squared, and therefore they have the real part. Okay, I have the zeros here. This is j omega n and minus j omega n. For the poles, the real part is minus zeta omega n. So I go a distance of minus zeta omega n on the left hand side. Then note the imaginary part. Imaginary part is less than omega n. It's not greater. Many of you, about 30% of the class, showed somewhere here at the top. No, it shall be less. It is somewhere here, where this distance is omega n multiplied by square root 1 minus zeta square. Some of you over enthusiastic
Omega n
ones.
minus this term.
Omega n minus so much.
So 1 minus
The distance is
Okay,
Basically,
distance from
One
the
that is right. So this is omega n 1 minus this. Thank you. Alright, this is j omega n and this is j omega n square root 1 minus zeta squared. So there is a difference between the two. Some of you over enthusiastic ones thought that zeta much less than 1 may have been called for. No, unless that is called for, why should you assume that? I didn't say zeta is much less than 1, and they said that poles and zeros are at the same point. Well, if poles and zeros are like that, then it's a very different situation. It's a very different situation, and we have to be careful about this. There is a slight difference because of zeta. And even if zeta is 0.2, zeta squared is much less than 1. That is correct. But it would not be correct to put the poles and zeros the same vertical level, because that changes the situation completely. Okay. The other part was give a rough sketch of the variation of magnitude and phase of the transfer function with frequency, clearly indicating the frequencies of maxima, minima and transitions, if any, and the values there. Okay. My transfer function is, now this is a part where I didn't find a single satisfactory answer. What I have to do is to plot the magnitude and phase with frequency, clearly indicating where this is maximum, minimum or transition. Transition obviously can occur in phase, not in amplitude. One of the mistakes that many people did was to draw the picking circle. The picking circle is not applicable here. Why not? Because the numerator is not a constant. It's only if the numerator is a constant. Even in the band pass case or the high pass case, the picking circle, as was done for the low pass case, was not applicable. So no question, no picking circle. No, you have to look at the expression. If you look at the expression, you see that h of j omega is equal to omega n squared minus omega squared divided by omega n squared minus omega squared plus j twice zeta omega n omega. Okay, this is the expression, and then look at the magnitude. H of j omega magnitude square, let's say, let's take the square. Now something will be obvious. Omega n square minus omega square whole square divided by omega n squared minus omega squared whole square plus 4 zeta squared omega n squared omega squared. And it doesn't take any special intelligence to observe that this magnitude cannot exceed unity, because the numerator is a whole square, it cannot be negative. The denominator, there is sum of two whole square, cannot be negative either, and this term is identical with this, so the denominator is always greater than or equal to the numerator. So this must be less than or equal to 1. In other words, the maximum possible value is 1. Now how can 1 be reached? That is the question. Well, for that either you look at this or you look at this. Let's find out at s equal to j0, that is at 0 frequency. 0 frequency, omega n squared by omega n squared. So the magnitude is 1. At infinite frequency, it is this term which dominates. This term which dominates. So infinite frequency also the value is 1. There is no other value in between where it can reach 1. And therefore the plot must start, the magnitude, it must start at 1 and end at 1. Also it is obvious that at omega equal to omega n the value is 0. So the minimum value is 0 at omega equal to omega n, and the maximum value is 1 occurring at 0 as well as at infinity. Okay, this is the magnitude plot. Yes, any question?
Isn't it differentiable at omega?
Is it differentiable at omega equal to omega n? No. There is a sign change, there is a discontinuity. You can see it from here, that omega, there is a phase discontinuity at this point. Okay? So it just comes like this and it goes like this. It's not a smooth curve. However, let me point out, if your output was taken across a real inductor which has a small resistance in series and a real capacitor, if the output was taken across this, then what would have happened is this sharp dip to 0 would have rounded off like this. Then it is differentiable. Okay? And there would not be a discontinuity in the phase. Phase would also be smooth. Now let's look at the phase. Is there any question on the magnitude? The magnitude cannot have, well, these are not strictly maxima or minima. Is that point clear mathematically? Highest value, these two are highest values, and this is the lowest value. Lowest value is not a minimum. But in electrical engineering, we use loosely. We don't care whether the slope exists or not. Okay, maxima and minima. It is in that sense that I use this term. Now let's look at the phase. I have omega n squared minus omega squared divided by omega n squared minus omega squared plus 2j omega n zeta. 2 or 3 of the students ignored this term, saying zeta is, oh, let me not tell you that mistake. Okay. About as far as phase is concerned, you notice that the numerator term is positive if omega is less than omega n, and is negative if omega is greater than omega n. Obviously there is a phase change at omega equal, there is a phase transition through 180 degrees. Okay, and if you had looked at the pole 0 diagram, okay, the poles are here, and you notice that if you draw the vectors, okay, this is one way. Let's say at 0 frequency, obviously the phase due to this 0 and this 0 they cancel each other, so the phase becomes 0. And then due to this vector and due to this vector, the two phases also cancel each other. So the phase starts from 0 at DC. At infinite frequency, well, all of them tend to infinity, all vectors tend to infinity, so again the phase is 0. In between, suppose omega is slightly greater than 0, alright, then this angle has decreased, whereas this angle has increased, and therefore the angle due to the two poles is positive, and the total angle would now be negative. Therefore, between omega and omega n, the phase is negative. What happens at omega equal to omega n?
180 degrees.
Minus 90 degrees.
Okay, if omega equal to omega n minus, not exactly at omega n, the phase
Pi by
becomes
Minus
minus pi by 2. And if you go to omega equal to omega n plus, the phase
Pi by
becomes
two.
plus pi by 2. And therefore, that's all that is required for phase plot. Therefore, the phase plot phi omega would be like this. It goes like this. Now, there is a problem here. There is a problem here about the curvature. Is it like this or like this? Tan inverse. It's a plot of tan inverse. And tan inverse plot is always like this. There is a curvature problem. Be clear about this. So, it goes to minus pi by 2. At omega equal to omega n, it goes through a phase change of 180 degrees. So, it goes to plus pi by 2, and then again it goes to 0. This is the phase plot. This frequency is omega n. Next, third part, very few people have attempted, and I thought that would be very simple. This concerns the half power frequencies. Now, obviously, the maximum power, if you look at the magnitude plot, obviously maximum power is at DC or at infinite frequency, maximum value of the magnitude function. And half power would therefore mean the frequencies at which the magnitude becomes 1 by root 2. It has nothing to do with omega n. It is not a selective response. It is not a high Q acceptor type of response. It is a rejection response. It has nothing to do with the value at this point. Value at this point is 0, and 1 by root 2 of 0 is also 0. So, the half power frequencies always refer to the maximum, okay, and the maximum is 1, and therefore you have to find out where the value is 1 by root 2, okay. And in order to do that, we look at the magnitude again. If you recall, h of j omega magnitude square, I am taking this square so that I don't have to work with square roots. It is omega n squared minus omega squared whole squared divided by omega n squared minus omega squared whole squared plus 4 zeta squared omega squared omega n squared. Is that okay? Is that okay? Now, obviously, half power frequencies will be reached when this term is equal to this term. You don't have to write this as half and then simplify. It should be obvious. When in the denominator both the terms are equal, obviously the magnitude squared would be equal to half, and therefore half power frequencies satisfy omega n squared minus omega squared whole squared equal to 4 zeta squared omega n squared, okay. And how many such half power frequencies shall be there? We want two, isn't it? Unfortunately, this is a quartic equation and it shall have 4 solutions, okay. 2 of them will be negative and 2 of them will be positive. It is the positive ones which you have to take, and the algebra simply shows that omega 2 1 shall be equal to omega n 1 plus zeta squared plus minus zeta omega n. This is the solution. Now let me tell you where you made a mistake. Those of you who attempted but didn't get it correctly made a mistake that they wrote one of the solutions is well, some of you wrote minus zeta omega n plus minus omega n square root 1 plus zeta square, in which one of the frequencies is positive, the other is negative. Isn't that right? The correct solution should be this, in which both of them are positive. You see, obviously this term is greater than zeta omega n, so both of them are positive, and this is the correct solution. The third problem concerns a double tuned circuit, but only in a very small part. Most of the problem concerns a single tuned circuit, and I do not know why it didn't occur to you that it's a problem concerning a single tuned circuit. Majority of the questions asked relate to a single tuned circuit. It is given that the current in a single tuned circuit attains a maximum value of 1 milliampere at 108 radians per second. What does that mean? It means that at the frequency, well, current in a single tuned circuit is R plus J omega L minus 1 by omega C. It is not proper to be conditioned by the circuit that we examined in the class. That is, we took the output across the capacitance. Voltage across capacitance is current multiplied by 1 by omega C. So, there is an additional factor, additional frequency term there. Whereas, this is simplicity itself, it is only the current in this circuit. Obviously, the current shall attain a maximum value when the reactive part is 0, and therefore, what is given is omega n 1 by square root L C is equal to 108 radians per second. Those of you who multiplied this by 2 pi made an unpardonable offense. It is given in radians per second, why should you multiply by 2 pi? So, omega n is given. It is also given that the maximum current obviously is reached at this frequency. The maximum current has to be V by R, and the source is 1 volt sinusoidal, and therefore R is equal to 1 K. Alright, the maximum current I max is given as 1 milliampere. So, 1 volt divided by 1 milliampere is obviously 1 K. So, the resistance is known. The other thing that is known is, under this condition, that is under current resonance, the voltage across the capacitor is 5 volt, which means that 1 milliampere multiplied by the impedance of the capacitor at that frequency, so divided by omega n times C, omega n is given as 108 radians per second. This is equal to 5 volt, from which you can find out C. And if you find out C, then you know what is L. The values, my calculation gives C as 1.85 microfarad and L as 46.295 Henry. I hope I am correct. So, I found out all the parameters of this single tuned circuit. Then it says, the second part says that this single tuned circuit is inductively coupled loosely to another identical single tuned circuit. Now, we come to the case that was discussed in the class, a double tuned circuit, and the output is taken across the resistance in the secondary. This is precisely the case that we dealt with in the class. Output is taken across the secondary. The magnitude response shows 2 peaks, one of which occurs at 110 radians per second. Well, one of which means it must be the upper peak. One greater than omega n is the upper peak, one less than omega n is the lower peak. So, and by simple manipulation we had shown that this maximum omega 2 m is given by omega n plus omega n multiplied by square root of k square by 4 minus zeta squared. This is a formula derived in the class, given in the book, figures in your notes. Despite all this, despite all this, I was shocked to see this as k square minus zeta square by 4. Those who have made this mistake know that this was a Himalayan mistake. And in an open book, open notes examination, no, sorry, it cannot be done. It should not be done. It's an offense. And all that we are given now is this is 110, this is 108, this is 108, k is not known, but zeta, how do you find zeta? Zeta is 1 over, okay, zeta is r by 12, zeta omega n equal to r by 12, from which you find out zeta. Well, the other way is, if you remember, in a single tuned circuit at current resonance, that is when the current is maximum, the voltage across either the inductor or the capacitor is Q times the applied voltage. Did you know this?
No, sir.
110.
No, sir.
Okay, it doesn't matter if you didn't know it, but now, at least now you should know it, and it's very simple to prove. You see, at current resonance, the voltage across the capacitor would be I resonance divided by omega n times C, and I resonance is V by R, and therefore this is V by omega n CR, which is equal to omega n times L, no, there is no R. Have I made a mistake? Okay, which is equal to omega n L by R multiplied by V, and you know this is the Q of the coil. So the voltage across the capacitor is Q times V. I am not complicating the situation. If you remember this, similarly you can show that the voltage across the inductor is also Q times
V is
V.
the maximum voltage of the applied.
V is either the peak value or the RMS value, it doesn't matter. Whenever you make a measurement, you measure the RMS value. Okay? Even if you take the peak value, it doesn't matter because you are taking ratios. Alright? So Q here is 5, and zeta, as you know, the definition of Q is equal to 1 by 2 zeta. So zeta is 1 by 2 Q. This is simply 0.1 because Q is given as 5. This was another alternative to finding the question. Yes, any other question? We will do a little bit of recapitulation first. If you recall the Y parameters, of the two port, well, the defining equations are I1 equal to V1 Y11 plus V2 Y12, I2 equal to V1 Y21 plus V2 Y22. And I think last time in the last lecture we had taken an example of the pi network, YA, then YC, then YB, and we said that by inspection you can see that Y11 is equal to YA plus YC. Y11 is the input admittance with the output short circuited. So YB goes out of consideration, YA comes in parallel with YC. Y22 is equal to YB plus YC, and either by applying the definition or by remembering the equivalent circuit, you can see that Y12 is equal to minus Y21 equal to Y sub C.
Y21 is equal to
Minus, both of them are minus. Minus Y12 equal to minus Y21 is equal to Y sub C. Alright. Now let us take a little more difficult example, that is we take the T network Z1, Z3 and Z2. We are required to find out the y parameters of this network, and we shall apply to find the y parameters of this network. We apply the general procedure. General procedure is at ports 1 and 2 you connect a voltage generator V1 and V2. Then write the mesh equations. Well, there are two meshes, I1 and I2. Write the mesh equations and solve for port 1 and port 2 currents. That is, here there are only two meshes, there could be more if the network was more complicated. You solve for I1 and I2, and that should give you the 4 y parameters. Let us do it. V1 equal to I1 Z1 plus Z3 self impedance plus I2 Z3 mutual impedance. V2 equals to I1 Z3 plus I2 Z2 plus Z3. So, from which I have to solve for I1 and I2. I1 obviously is V1 del 1 by del plus V2 del 2 by del. This should be remembered, and the current I2 is V1 del 2 by del plus V2 del 2 by del, where del is the impedance matrix, del is the determinant of the impedance matrix Z1 plus Z3, 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 Z2 plus Z3. And by comparison you see that Y11 is del 1 by del and so on. Therefore, Y11 would be equal to del 11. So, first row and first column goes. So, Z2 plus Z3 divided by del. Similarly, Y22 is equal to Z1 plus Z3 divided by del. Y12 which is equal to Y21 shall be equal to del 21 or 12 by del, and the sign shall be negative. So, minus Z3 by del. Okay. Now, if any question? If this T network is to be equivalent to the pi that we had drawn earlier, okay, if this is to be equivalent to this network YA, YC, YB, okay, then obviously what we should do is we should equate this to what? YA plus YC. We should equate this to YB plus YC, and we should equate this to what? Minus YC. Alright, and therefore we find the values of YA, YB and YC. YC is simply Z3 by del, YC is Z3 by del, no minus, it is plus because this is minus YC, this is minus Z3 by del. YA would be equal to Z2 by del and YB shall be equal to Z1 by del. These are the formulas for T to pi conversion, T to pi, alright. Z1, Z2, Z3 are parameters of the T network, and YA, YB, YC are the parameters of the pi network. So, given Z1, Z2, Z3, these are the formulas for finding out the parameters of the pi network. We had done the reverse case earlier, that is how to convert a pi to a T, alright, and the two together are extremely useful in network analysis and to electrical engineers in general. We shall close here.